Okay, so this session is going to be about FTC Road Runner, and this is a workshop, uh, the second workshop of three, um, and we're going to get started. Some things about me before we get started. Uh, I've been part of FIRST for 7 years. This is my second year in FRC, and the past 4 years before that, I was in FTC. And the year before that, I was in FLL. I love programming. I've been coding leads for my teams. I know Java, Python, uh, React.js, the whole bunch of languages. Um, and I also have a YouTube channel where I show things like this or showcase my projects and help you learn some things. So that that's right into. So, so FTC is so FRC, which I know you're familiar with, is where we build those robots, bigger robots, and we have almost a basketball-sized field where we have a field and we do different objectives. Um, and while FTC, it's more, um, it's about a 12 foot by 12 foot robot, and it's similar to FRC where we have the different objectives we have to do, but it's just on a smaller scale and it's a little slower, right? Since you don't need to go as fast. Um, so that's kind of the gist of it. Is that good? And also, uh, post my YouTube channel on the chat. Give me 1 moment. Uh, uh, um, okay, so so getting so what Roadrunner is um, what Roadrunner is, it's a motion planning library for FTC. So what this means is that, well, what you might be familiar with in FTC is maybe saying coding a function in your robot to say move 40 inches forward, and you do that by um, calculating your motor gearbox gear reduction, and then based on that, you know how much a rotation translates to how far you go. But the advantage that Roadrunner gives is two things. So it allows um, for a more tuned and more precision way of doing that, as well as with that giving you abilities to um, giving you abilities to make a, for example, spline or different types of trajectories. So going over later this session. So it allows you to, for example, consider speed limits, accelerations, and different obstacles around the way where you can pathfind around it as well. So, um, so Roadrunners has many features where it has consistent performance, where it due to the tuning you do beforehand, it allows you to have much more consistent and matches where you're able to have your autonomouses hit your marks every single time. And um, again, I was talking about the spline trajectories, where we're able to make a curved route, and that way, for example, if your robot needs to take a 90-degree turn, instead of slowing down to a stop and then turning, the spline trajectories allow for a smooth curve so that you don't need to slow down and you can keep going. Um, and using advanced control, we also have built-in velocity, acceleration, and jerk constraints to prevent the wheel from slipping and overshooting. And that's really important in this case because it allows us to be accurate in our autonomouses. And that may be an issue where if we're just driving by power, time, using that distance calculation that I was talking about earlier, the robot sometimes just doesn't know where it is, right? So this is what it allows it to be. Um, so it has trajectory building using the splines turns, and then we can add on to it again and again to make a more complex autonomous and do more features. Has the motion constraints, and it also uses PID and feed forward, which we'll be going over this section because it's really important to understand the math behind it. Um, Even though math may be, uh, I guess, boring or hard, I'll try to make it as simple as possible. But understanding the math allows you to understand what you're actually doing in the PID tuning process and how you can apply that correctly. So before we get into that, we need to understand um, the almost coordinate system we're working with. So in school, you might have learned the Cartesian coordinate system or just a normal graph, x and y. So or y and x. But uh, this the FTC field, once you look on it from the top, it pretty much is a x and y graph, right? We have the x and y on the flat, and then z, which is 3D or height, is the height, right? Um, so it can be pretty simply broken down to that, and then based on that, we're able to say, well, I want to go to this specific position, and that really makes our abilities uh, very large because then instead of having to program each move forward, move left, things like that, we can simply say go to this point and it'll go for us. So let's go over some of the meanings of what PID stands for, it means, and the math behind it. So PID stands for proportional integral derivative. So let's first go over proportional. So P, it fixes the error based on how big it is. So if I go to a graph here, so once we set a set point, so let's say that on here, the y-axis is, let's say we have an elevator, right? And our y-axis is the height of the elevator. So let's say this is our set point, so let's say 50 inches tall. And then our x is our time. So what the p-value does is it is the pushing force, right? It moves the function forward based because when we're at time 0, we're at position 0, and it's able to calculate with our formula. It's Kp and then the change in E. So Kp is a constant, and that's basically saying, well, beforehand I tuned it, and I said that, let's say Kp, the um, constant of the proportional, was 0.2, 0.25. And then this means the change in E. The change the change in E means the change in the error. So the error is the distance from our current point, so at time 0, we're at distance 0, or point, or at height 0, and then our set point was 60, I believe it said, or we can say 60, right? Um, so at time, uh, so then that our distance we have is, our error is 60. So that means that our change is what's it, 60 minus 0, because um, and then that is times the uh, the constant, and that means that it's going to feed that motor that much more power, because the larger the error, a change in error, the more the proportional will be. For example, if it was just an error of 2 inches, right? Um, because it would be 0.2 or 0.25 times 2, that the power fed into a motor controlling the elevator would be much less than if the error would be 7. Then, um, if we jump to D, which is derivative, what it's looking at is how quickly the error is changing. So in practical terms, what this is doing is, as it approaches the set point, it's going to be dampening the power of P. So the proportional can sometimes be very, very high, and because of that, it's going to overshoot. So as you see in this red line here, um, the proportional in this case would be too high, and it would shoot over the set point, which is bad because you're going to stop at that set point, and then because it has too much momentum, too much power, and then it's going to oscillate around it. So that's bad because in real life, our elevator would go up and then down, and then it'll do like this, which would be bad for the motors, bad for speed, and um, yeah, you'd lose a lot of time. Uh, so what the D derivative allows it to do is it dampens the effect of P. And the way it does that, um, is by using derivative. But in simple terms, so in this equation, PD is our constant, our derivative constant. Same thing like the Kp we had before of being 0.2, we tune it by ourselves. And based on that, we multiply it on the change in E over the change in T. So D would be the change in this case. Um, so what this means is the change in E, meaning the change in the error, over the change in time. What is that? That's the slope, right? So if we have a very high slope, mean, uh, if we have a negative slope, then that means that we're going to be decreasing the error is decreasing at a very high speed, and therefore um, it's going to give less power because our slope. So let's say that so in simpler terms, we can write this equation like this. So we'd be able to write uh, the so our this is our constant we've tuned by ourselves, and then that's times uh, the change in the error divided by the change in time, right? And otherwise, you can also, if you're not familiar with delta, which is the change in, you can also write that in T parentheses. That we can say the before error, uh, or we can say the uh, current minus the past error. And then that's the same thing with the time. So and time minus the past time. So in simpler ways, this is simply just a slope equation. So in our graph, if this is time, and then this is our error, if the if the error is decreasing, meaning the distance between the set point and our current point is decreasing, meaning like let's say that up here was our 60 inches point, our error of 60 inches, and then down here that's 0 inches, right? So it's our error is slowly decreasing, and that's different from this graph here where that's our set point, and on our y-axis we're graphing um, our current point, our current height. So when the slope is decreasing, as in this case here, or negative in other words, our it would be PID, which is our constant again, times a negative slope. And that means that we're going to be decreasing the effects of P and I, which we'll talk about next, um, by subtracting it out of the motor's power. Because the way that PID works is um, the values from the P equation plus the I equation plus the D equation is equal to what power is given to our motor. So, um, because we're going to have our P equation, our linear P equation here, um, and again, the change in E in this here, also in the linear equation, is the same as what's described here with the current error minus the past error. So plus the I, which we'll talk about next, plus the D equation, which is this. So all of that is being added together. So if this D, the derivative equation, is negative, and this is positive, it's going to reduce the effects of it. So then next, uh, so then yeah, that creates the dampening. That's how the dampening effect that's it's being created. Uh, so and then I, we generally you don't use it as much as P and D. So um, then the use case of it would be, um, let's say that uh, your elevator always goes to 59 inches when it's being set to 60 inches. So, or in any place, like, or if you're going to 70 inches, it always goes to 69 inches, and so on. So there's always that bit of error that you're not able to uh, get rid of, because if you increase the P too high, that means that it'll start to oscillate on the graph because it'll be overshooting again and again. And then the D, the derivative, would not help because all that would do is it would slow it down even more before you get to it. So that's the use case of it, and the meaning is um, it's using an integral, but it's saying that it's accumulating all of the errors in the past, and then it's multiplying it by the change at the time, and then that's being multiplied to our constant. So um, uh, that's a short overview of it. Uh, but so this is what our PID system would look in a uh, in an system, right? So we have our PID, and then we plug into it our current position, right? Because our PID takes in our error, which is the distance between our set point and our current position, and we plug it into the PID, and then the summation of all of that, like we explained here, is then outputted into a motor, and then the sensor on that motor will loop back to our initial PID uh, controller, and then say, well, now my current position is 50 inches, and before I was recording 40 inches. So, and our set point is 60 inches. So now the error is 10 inches. So it's a continuous loop, and it's again and again going um, and running until it's at its state, while it's at the set. Um, did you understand that? Okay, Andrew. Yeah. Any questions about it? So, so sorry, can you say that again? Um, there won't, but there'll be one next week on Tuesday. Sorry. Well, we can uh, we can have workshops inside the pub meetings as well. These are just more general. Okay, so now we can go over some of the code of um, how we would use the spline trajectories or the strafing for in our robot. Um, so what we'd do is we'd define a trajectory, and we would have our drive object, and with that we'd do dot trajectory builder. And what this allows us to do is we first input our initial pose, and then we make a spline or uh, whatever other uh, you input whatever other uh, movement you want, and then you do dot build. So in this case, we would say spline2 and new vector 2D, and then 30 inches and 30 inches. So those would be 30 inches to the right and 30 inches in front. And then we also want to turn 90 degrees. So math.to radians would just convert our 90 degrees to radians. And in this case, we would go, the spline trajectory would create a similar path where we would turn, and it would move in a curved direction. And again, that stops the need for needing to go forward, decelerate to a stop, rotate and then move forward. Um, so you have other ways to do this as well. So other functions as well. So you have forward if you just want to say I want to move forward 30 inches, or vice versa, move back 30 inches. Um, Also with strafe left and right, you can it works the same way. The line2 function allows you to do same way as spline works, except instead of making this smooth path, it would go directly through. So it would just go if it would if this is a robot and this is the spline trajectory, uh, then the line2 function would just go straight to it. And then uh, turning works self-explanatory, except remember it's in radians. So if you wanted to turn, for example, 90 degrees, you would say math dot 2 radians 90 degrees. Or you could say uh, pi over 4, which would be the what's it in radians. And then you also have spline to linear heading. What this will do is it just keeps your heading the same while it drives. But that'll pretty much wrap our session up. Um, so what we learned some stuff. So we learned a lot about PID algorithms. So we got to learn the math behind that, and then we also got to get into some of how to express the different trajectories in Road Runner. Are there any questions about anything, whether it be the PID or uh, the vectors or our splines? Yeah, um, so this is for programming for FTC. The last one last week was for CADing, and then the last one is about scouting for FRC. And scouting is a scouting is an important part of FRC where we do data collection and analysis on robots during their matches, and that allows us because the way FRC works in our competitions is the first uh, it depends on the size of your competition, but let's say the first 40 matches are randomized. They're called qualification matches. Um, and then based on that, however, how good you do, you get ranked, and then the top 12 alliances, uh, or the top alliances, would be able to pick their own team, other teams to be on their alliance or team, and then they get to compete in a playoff style bracket. So scouting allows us to get those informed decisions to say, well, this robot is really good at, let's say, last year's FRC game, really good at L4 coral scoring. Um, so that means that they should pair up with us because we're really good at L2 and T uh, coral scoring. Does that answer your question? Um, so I'm gonna send uh so yes. So I'm gonna send out a survey about our session. So I'll send that in 1 second. Okay, so I posted that survey in the chat. If you if you can fill that out, that'd be helpful for me. And also my YouTube channel is still in there, so you can subscribe. Um, than that, well, thank you for attending the workshop, and I hope you got some knowledge out of it.